cover 3 learning objectives. We'll discuss functional groups, alkanes and alkane isomers, and alkyl groups. What is a functional group? It's a collection of atoms at a site that have a characteristic behavior in all molecules where they occur. And if you look at a lot of different organic chemistry textbooks, you will find in the table of contents that the material is divided by functional group. So it's common for us to approach organic chemistry from a viewpoint of functional groups. There are these collection of atoms within molecules that have predictable reactivity. For example, double bonds in simple and complex alkenes will react with bromine in the same way. So if you have a simple alkene like ethylene, or you could have a double bond in a more complex structure like this one shown on the right, both of those double bonds react in the same way when they react with bromine. So you have a double bond here, and then you end up with 2 carbon-bromine bonds in the product. So even though they differ by a lot of other atoms, the fact that they both have that double bond allows us to predict how that double bond will react with particular reagents. An alkene is what we call a carbon-carbon double bond. A carbon-carbon triple bond is given the name alkyne, and an arene, or an aromatic ring, is a ring with alternating double and single bonds. Now I'm going to go through a list of different functional groups, and I recommend that you make flashcards because you want to commit these to memory. So alkene, alkyne, and arene I already discussed. A halide has a carbon-halogen bond. An alcohol has an OH group attached to a carbon. An ether is defined by this carbon-oxygen-carbon pattern. A monophosphate has this PO4 group. A diphosphate has 2 of those. An amine has this carbon-nitrogen single bond, and the nitrogen also has 2 other groups attached. An imine, IMINE, has a carbon-nitrogen double bond. A nitrile has a carbon-nitrogen triple bond. A thiol has a carbon bonded to an SH group. A sulfide has a sulfur between 2 carbons. A disulfide has a sulfur-sulfur bond, and each sulfur is further connected to a carbon. A sulfoxide has a sulfur-oxygen bond, which is often depicted as a double bond. These are resonance structures. It turns out that this structure on the left is a very predominant structure in the overall hybrid, but you will find people drawing them often more like this than the charge-separated structure. But a sulfoxide has a sulfur-oxygen single bond if drawn like this, or a double bond with carbons on either side. An aldehyde has a carbon double bonded to an oxygen, a carbon on one side and a hydrogen on the other. A ketone has a carbon-oxygen double bond with carbons on either side. A carboxylic acid has a carbon-oxygen double bond, a carbon on one side and an OH on the other side. An ester has a carbon-oxygen double bond. So notice all these carbon-oxygen double bond containing functional groups. We actually give the carbon double bonded to an oxygen its own name. It's called a carbonyl. So if you have a carbonyl connected to an oxygen connected to a carbon on one side and a carbon on the other, that's called an ester. If you have, instead of an oxygen, a sulfur there, that's called a thioester. Thio just means sulfur. An amide has a carbonyl with a carbon on one side and a nitrogen on the other. An acid chloride has a carbonyl with a carbon on one side and a chloride on the other. A carboxylic acid anhydride, or sometimes just called anhydride, has 2 carbonyls connected together by an oxygen with carbons on either side. If we look at all those different functional groups, we can put them into certain groups. So one group you could put them into is a carbon singly bonded to an electronegative atom. And the functional groups that fit that are shown here. So you've got the alkyl halide, the alcohol, the ether, the phosphate, the amine, the thiol, the sulfide, and the disulfide. So in all of these, you have a carbon singly bonded to an electronegative atom. Now you might be thinking, hold on, sulfur is not that much more electronegative than carbon. And you're right, which if you look at the electrostatic map, you can see that there's just a slight buildup of charge on the sulfur atoms. Another group to consider would be all of the groups that contain carbon-oxygen double bonds, or carbonyl groups. So here you have the aldehyde, the ketone, the carboxylic acid, the ester, the thioester, the amide, and the acid chloride. An additional note on amine functional groups is that we can further classify them as primary, secondary, or tertiary amines. This is our example of an amine. They are all derivatives of ammonia, NH3, where we've replaced one or more of the hydrogens with carbon-containing groups. If we've replaced just one of the hydrogens, we call that a primary amine, which we symbolize with 1 and degree symbol. If we've replaced two of the hydrogen groups, that's called a secondary amine, which we abbreviate as 2 degree symbol. And if all 3 hydrogens are replaced, then that's called a tertiary amine, or 3 degree symbol. Now let's practice this. So here is the compound called methionine. That's an essential amino acid. Can you find the functional groups in this molecule? So right here we see a sulfur, and I'm going to redraw this in a bond line structure. So carbon, sulfur, carbon, 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 C double bond O, OH, NH2. And I'm going to number these carbons just so we make sure that I drew it correctly. So 1, 2, 3, 4, 5. So that will be 1, carbon 2, 3, 4, and 5. So yes, I accounted for all of my carbons. So here I have a sulfur bonded to carbon on either side. That's a sulfide. Here I have an NH2 group bound to carbon 4. That's an amine. And in particular, that's a primary amine because it's just bonded to one other carbon and it has 2 hydrogens on it. And then over here, notice that C double bond O, and it has an OH on one side and a carbon on the other. That is a carboxylic acid. Alkanes are compounds with carbon-carbon single bonds and carbon-hydrogen bonds. Connecting carbons can lead to large or small molecules. They're often also described as saturated hydrocarbons, and sometimes they're called aliphatic compounds. This alkane is the simplest alkane. It's called methane, and it has 4 hydrogens singly bonded to carbon. Ethane has 2 carbons and 6 hydrogens. Then you have propane and butane. The formula for an alkane with no rings is CnH2n plus 2, where N is the number of carbons. And we say that alkanes are saturated with hydrogen, meaning each carbon has the maximum number of hydrogens it possibly can have. There are a variety of alkane isomers. There are straight chain alkanes, which are just alkanes with the carbons connected to no more than 2 other carbons. Sometimes you'll see these called normal alkanes. There are branch chain alkanes, where you have alkanes with 1 or more carbon atoms connected to 3 or 4 carbon atoms. And sometimes you have isomers that are straight chain alkanes and branch chain alkanes. But to define isomers, that just refers to compounds that have the same number and kind of atoms, but they differ in the way that the atoms are arranged. And there are spatial isomers called stereoisomers, and there are constitutional isomers. Constitutional isomers, they all have the same formula, so they have the same number of carbons and hydrogens, but the way that those atoms are connected together differ. So there are 3 different constitutional isomers that have the formula C5H12, and they are drawn here. So I'm going to draw in the numbers of the carbon atoms. 1, 2, 3, 4, 5, just so you can verify they all have 5 carbons. 1, 2, 3, 4, 5. Now what's different about these? It's the way they're connected. One way we can analyze them is determining whether the carbons are primary, secondary, tertiary, or quaternary. So a primary carbon is one that has just one other carbon attached to it. So this carbon is an example of a primary carbon. A secondary carbon has 2 carbons attached to it. A tertiary carbon has 3 carbons attached to it. And a quaternary carbon, say that 10 times, has 4 carbons attached to it. And we can use the number with the degree symbol as a shorthand for those terms. Now let's look at the 3 isomers. So with the isomer on the left here, it has 2 primary carbons in the red boxes. The one in the middle has 3 primary carbons, and the one on the end has 4 primary carbons. So this just shows you that they are definitely different because they have different amounts of primary carbons. Now what about their secondary carbons? So in this structure, which would also be called a straight chain alkane, because notice no carbon is connected to more than 2 carbons. 3 of the center carbons, these carbons, are secondary carbons. They're connected to 2 other carbons. This one here just has 1 secondary carbon, and lo and behold, this one on the right doesn't have any. Then when we get to tertiary carbons, only this structure has a tertiary carbon, which would be this guy. It's bonded to 1, 2, 3 other carbons, so it's tertiary. And then only the structure on the right here has a quaternary carbon. So this carbon right here is connected to 1, 2, 3, 4 other carbons. Here are just some more examples of constitutional isomers. So you could have different carbon skeletons with the formula C4H10. It could look like this, which is called 2-methylpropane, or like this, which you know as butane. But you can also have constitutional isomers of things other than just alkanes. So if you have this formula, that could form ethanol. So that would be an alcohol functional group, or it could form an ether. So you can actually make different functional groups from the same formula. You could also have a different position of functional groups. So with this formula, you could have an amine where the nitrogen's connected to the center carbon, but here the nitrogen's connected to the carbon on the right side. Sometimes you will see alkanes written in a condensed structure, which looks like this. And it doesn't show any bonds, but it just lists the atoms. And sometimes if there are groups that are repeating, that's indicated by putting the group in parentheses and indicating a number outside the parentheses showing how many of those groups are repeating. So butane could be written like this in condensed formula, or this. This would be the Lewis structure. This would be the Lewis structure in the staggered conformation that illustrates the tetrahedral geometry around each carbon. Sometimes you might see it drawn like this. So there's a variety of ways that alkanes can be represented. There are names for straight chain alkanes, and you want to memorize at least through 12. Methane is an alkane with just 1 carbon. Ethane has the formula C2H6. Propane has the formula C3H8. If you have 4 carbons, it's butane. 5, it's pentane. 6, hexane. 7, heptane. 8, octane. So notice all these have the ending ANE. 10 is decane, 11 undecane, and so forth. Now there's also something that's called an alkyl group. That's a partial structure that remains after the removal of 1 hydrogen from an alkane. These are not stable compounds, but they're parts of larger compounds, and when we get to naming, we will be referring to alkyl groups. So methane is CH4. If you remove a hydrogen, that's called a methyl group. So the ANE becomes a YL. So this little squiggly means that's the point of attachment to the rest of the molecule. And this ends up being important in naming. So this molecule is called methyl alcohol because you have a methyl attached to an alcohol functional group. This compound is called methylamine because you have a methyl group attached to an amine. So for straight chain alkyl groups, you just again change the ANE ending to YL. So butane becomes butyl, pentane becomes pentyl, and so on. The final thing we want to do is learn how to draw constitutional isomers. And this is an iterative process, but there is a strategy to it. So first you want to just draw the main chain. So with the number of carbons that you have, draw them all out in a single chain. And then put in your hydrogens. That's your first structure. That's the easiest structure to draw. Now for the next structure, draw the main chain minus one carbon and add that methyl group to as many positions as possible. And try not to repeat structures. At first you will probably repeat structures you won't think you are, but then you'll realize you've just drawn the same thing that you drew before. But that's okay. You can just cross one off and keep on going. Then the next step, number 3, would be draw the main chain minus 2 carbons and add 2 methyl groups to other carbon positions on the chain, or try adding a 2 carbon group and ethyl group to as many positions as possible. And then you just continue subtracting and adding groups in this fashion until you run out of carbons. And once you've drawn all of your structures, you can figure out if you accidentally drew the same one twice by naming it, and we'll cover naming in the next video. But if the name is the same, then you know that you have drawn identical structures. Let's practice. Draw 5 constitutional isomers for C6H14. So you might want to pause the video and try this on your own and then resume the video. So first I'm going to draw all 6 carbons in a chain. 1, 2, 3, 4, 5, 6. And for this exercise, I'm going to go ahead and draw out my hydrogens, even though I know with bond line I don't normally draw out the carbons and the hydrogens, but it's going to help me in this particular exercise. Okay, so now I've got a formula of C6H14, and I have indeed drawn 6 carbons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So I need to draw 4 more constitutional isomers. So I'm going to draw 5 carbons this time. And I'm going to take this last CH3 group on the N, and I'm going to place it on carbon 2. Now I'm going to add in my hydrogens. If I had placed it on carbon 1, I would have actually just drawn the same structure that I started with, which is an easy mistake to make. If you do that, you just have a duplicate. It's not a big deal. So here I have 1, 2, 3, 4, 5, 6 carbons, but this isn't connected the same as the first one. Notice that with the first one, I just have primary and secondary carbons, but here I have a tertiary carbon. So that's definitely different. So I'm going to do the same thing again, and I'm going to try putting that CH3 group on the center carbon. So right here. Now I put in all of my hydrogens. Okay, and this also has a tertiary carbon, but the CH3 group is at the, if I were to number these carbons, 1, 2, 3, 4, 5, is at the 3rd carbon, whereas in the structure I drew above it was at the 2nd carbon. So those are not identical. Those are different constitutional isomers. Another way to think of it is if you look at the tertiary carbon, what kinds of things are connected to it? The tertiary carbon here is connected to a 2-carbon chain on the left and the right. The tertiary carbon here is connected to a 3-carbon chain on the right and a 1-carbon group on the left, and then they're both connected to a CH3. Now that's pretty much all I can do with moving a CH3 group along the chain. So let me try moving a 2-carbon group, an ethyl group, along the chain. So again, I'm going to draw out my carbons, but this time I'm going to cut off 2 of them. And I'm going to take the 2 that I cut off and I'm going to add them here like this. Now let me add in all of my hydrogens. Okay, first let's make sure we have the right number of carbons and hydrogens. 1, 2, 3, 4, 5, 6 carbons, we're good there. Then we've got 3, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Okay, so we definitely have the right number of carbons and hydrogens. Did I draw a duplicate of something I've already drawn, or is this indeed different? Looking at the primary tertiary analysis can help. So here I have a quaternary carbon. It's a carbon connected to 4 other carbons. I don't have that in any of the other structures, so I can feel pretty confident this is indeed a new constitutional isomer. So that gets me up to 4 constitutional isomers. There's a total of 5, so I just have one more to figure out how to draw. So I'm going to stick with my 4-carbon chain, and I'm going to add 1 carbon to the 2nd in the chain and another carbon to the 3rd in the chain. And then I'm going to add in all of my hydrogens. So first I'm going to count up my carbons and hydrogens, make sure I didn't accidentally delete something. Okay, yes, I've got 6 carbons, and I've got 3, 6, 9, 12, 13, 14 hydrogens, so I'm good there. Now I need to see, did I draw a repeat of something I've already drawn? Well, let's see here. We've got a tertiary carbon here and a tertiary carbon here. Did I draw anything else that has 2 tertiary carbons in it? Nope, nothing else I drew does, so this must be a distinct molecule. And this can be a frustrating exercise, but it can also be kind of fun because you get to try to connect the carbons in different ways to get new isomers. It's all about your approach. Just think of it as a puzzle to solve and try to have a little fun with it.